Thank you very much. Thank you very much for the introduction, and also thank you for inviting me to this nice conference. And my topic is somehow closely related to homological mirror symmetry, but not quite about it. So maybe more closer to enumerative mirror symmetry. And this is somehow part of this talk is joint work with Coates and Corti and Sen. You can find 0725. You can find it on archive, and also some my own work in preparation. And so first I'd like to review or maybe introduce the gamma structure, or what is the idea, basic idea about gamma conjecture. So I gave some talk last week, but I don't, of course, assume somehow the knowledge about gamma structure. So let me recall the quantum connection. So this is also called the Brovin connection. And this is the following thing. So, so let H denote cohomology group. Maybe I only consider even cohomology group of a symplectic manifold X. And then I consider the vector bundle H cross C, and with Z plane to H cross C, Z plane. And this is just a vector bundle on a vector space. And then I introduce the following connection. So, so let just tau I denote coordinates on H, and phi I be a dual basis. So I pick out some basis on H and then consider some dual coordinates tau I. Maybe if people cannot see this, please let me know. So then the connection, I introduce a connection of the following form. So this is somehow very famous connection due to the Brovin. And I use a quantum product at tau. And also, this connection can be also extended in the z direction. BDZ z square E star tau plus mu. And so this is some flat connection on a vector bundle, trivial vector bundle H cross H times C star CZ. Z is a coordinate on the C plane. And then, and here maybe I should say E is Euler vector field. So this is is something first gen class plus some correction which is only relevant in big quantum cohomology. So this is basically just first gen class, and mu is a grading operator. So mu is a grading. So 1/2 of the degree minus half of the dimension n. Sorry. So n is the dimension of x, complex dimension of x. N is a complex dimension of x. And then, so this connection is flat, but this has some singularity as z equals 0. And maybe I would like to notice that this has pole of order 2 at z equals 0. And somehow this is a quantum connection. And on this quantum connection, we can define some structure which is called gamma structure, gamma integral or gamma rational structure. Maybe I just call gamma structure. So, which is the following. So, let K naught of X denote a topological K group. K group. That is a Grothendieck group of topological vector bundle. And then I define a map from topological K group to the space of nabla flat sections of this de Broglie connection or quantum connection. Then I get, then this map is defined as follows. So I send any vector bundle V, class of vector bundle V, to the following thing. So SV of tau Z. So tau and Z are coordinates on H cross C, and which has the following asymptotics. So e to the minus tau on Z, Z to the minus mu, Z to the first Chern class of X. Sorry, there's some prefactor, and oh, maybe I also forgot that there's some normalization constant, which is asymptotic to this one. So times, sorry, times the following. So I have the so-called gamma class of X multiplied by 2 pi modified version of Chern character. So, so this is a formula. No, this is tau goes to large radius limit in general. Yeah. So in Fano case, you can replace the limit with z goes to infinity limit. So I'm going to just write the. So this is as tau goes to the large radius limit. So that means, this means that for any effective curve, the second degree part of d, tau, sorry, goes to the real part of this goes to minus infinity, and the somehow, if I write tau is second cohomology class plus other thing, then tau dash also goes to 0. So this is a large radius limit, and where somehow this is a limit where somehow in quantum cohomology the contribution from non-trivial curves die. So this is a limit where, for example, quantum product goes to the classical cup product. And so the formula looks a little bit complicated, but the essential factor is the second factor, where somehow you have this gamma class and 2 pi I version of Chern character. And this and the reason why we have this gamma factor is the following. So so you can think of this gamma as is a square root of third class. Third class. So maybe I didn't explain what is gamma, but gamma hat, this corresponds to this gamma function, gamma 1 plus x. So in the same way that this third class corresponds to x 1 minus e to the minus x. So third class corresponds to this power series. And in the same way, gamma class is defined in terms of this power series expansion of gamma function at 1. So, so for example, if you recall this famous identity, gamma 1 minus x times gamma 1 plus x, this is equal to pi I x and 1 minus exponential minus 2 pi I x e to the minus pi I x. So up to this somehow exponential minus pi I x factor, this is third, and this is square of gamma. So in this sense, this is a square root of gamma. And moreover, you can also see that somehow this flat section associated with this vector bundle. So if you consider this, the following pairing. So this is a Poincare pairing. If you take a Poincare pairing, like this, then this gives you exactly the Euler characteristic of V and W. For example, if V and W are holomorphic vector bundle, then you have this formula. So this is some alternating sum of dimension of the X2 groups. So, somehow this is the role of this gamma class. And the gamma conjecture in the title is the following conjecture. So e to the minus, where? In the formula that you just wrote. This one? No, just for the there? Yeah. E to the minus pi I z, yeah. This is, yeah, that minus z, but somehow this section is multi-valued, so I need to specify the path of analytic continuation. So that so it is a little bit confusing, but it is minus z, but somehow clockwise analytic continuation. So so now gamma conjecture. This is the following conjecture. So so this is somehow in a paper of Katarkov, Kontevich, Pantev, and also later in our paper is Galkin, Golishev, myself. And maybe Katarkov, Kontevich, Pantev did not say in this way, but somehow this is, I think, somehow what they wanted to say. The gamma structure, maybe gamma z or rational structure, is compatible with the Stokes structure. Stokes structure of this quantum connection. And maybe I don't tell you what is the Stokes structure here, but somehow because you have the polar border 2 at z equals 0, you have some irregular singularity of this connection, and then you have some Stokes structure, somehow depending on how flat sections behave near z equals 0. What is the growth order of the flat sections near z equals 0? This gives you some Stokes structure, and that should be compatible with this structure. And somehow this conjecture is somehow holds if for example, you have a mirror symmetry. And moreover, somehow kind of the Robin conjecture, maybe plus, somehow this also, this Stokes structure somehow is related to perhaps some decomposition position of, could be related to derived category of coherent shifts. And so this is maybe kind of generalized the Robin conjecture. So, today I'm going to talk about this kind of structure, these conjectures for toric associated with the toric flips. So, so let me review first maybe basic things about toric mirror symmetry. Maybe I should. So, toric case. This is somehow well-known mirror symmetry due to Given et al. And also Horibaffa and many others. And so let me just, for example, we consider X is P2. This is the simplest example. And maybe P1 is more simple, but P2 is the second simplest one. And this is mirror to W, which is W I denote by WQ, which is X plus Y plus Q on XY. So so this you can see from the fan diagram, basically. So you write the fan picture and then take a primitive vector. So this is a fan for P2, and you take a primitive vector for each one-dimensional cones, and then each primitive vector corresponds to monomial in these things. Then I have the following statement. So if we consider quantum cohomology of P2, this at some scalar parameter Q, this is isomorphic to the Jacobian ring of W sub Q. So isomorphic to W sub Q. And so Jacobian ring is somehow, in this case, just quotient of this ring with by the ideal generated by derivatives of W. And this is the first statement, and where somehow this Q corresponds to the some exponential of tau second. So this is a usual Novikov parameter or Kähler parameter appearing in quantum cohomology. And in my talk, I want to consider somehow D-module version because I'm discussing gamma conjecture. So if I want to lift these isomorphisms to quantum connections, then then what I get is the following. So the second isomorphism is quantum connection associated P2. This is isomorphic to maybe, today I call it a Saito structure. So WQ. So maybe last week I call it TEP structure, but so this is something defined to be, this is somehow some kind of quantization of Jacobian ring. So this is in this case, this cohomology with respect to twisted drum. So ZD plus DWH. So twisted drum cohomology. And this, on this side, you have, again, some connection, the so-called Gauss-Manning connection on the right-hand side, and that matches with the quantum connection on the left-hand side. So this is a toric case, mirror symmetry. And for the purpose of my talk, I want to consider some partial compactification of this picture. So partial compactification. Of this equivalent and Hori-Buffer mirror, which is somehow obvious compactification. So what I'm considering the following. So now I put U1 to be X, and U2 to be Y, and U3 to be Q on XY. I just put it this way. Then obviously somehow product of U1, U2, U3 is Q. And then I consider the following diagram. So C3, this is a space with 3 variables, U1, U2, U3. And then I have map W to C, and you have another projection to the Q plane. So
Z equals 0 there is
yeah,
the Jacobian,
right, exactly, yeah. Yes. So as you can see from this definition, you can see that it is Jacobian ring. Right. So I didn't say that. Yeah. So this is a limit. Z goes to 0. And Q somehow is, this vertical map is just given by the product of 3 variables, U1, U2, U3. And somehow you can think and I would think somehow this is compactified in the sense that originally Q was exponential variable, so it is non-zero, but now throwing Q equals 0. And actually, I want to think of this as some yeah. Yes?
When it was up there, it appeared as if somehow either I'm supposed to fix Q or treat it as an additional variable. So, but now I don't understand how if U1, U2, U3.
Yes. So somehow you fix some value of Q and then look at the fiber. And if Q is non-zero, this is a previous picture. Yeah. So this is just some very simple thing. So then I want to consider some partial compactification across Q equals 0. Now, and then I want to look at this family as somehow log smooth family. Somehow we put log structure at q equals 0, the standard log structure associated with a divisor, and then also put log structure on C3, somehow union of 3 planes. And then somehow this family is somehow smooth in the sense of log geometry. Then somehow you can compute this log Jacobian ring of W, relative, in a relative sense. So that is just, maybe this is just UI is quite elementary thing, but so I just consider the ring, the quotient by the ideal generated by this somehow logarithmic vector fields somehow along the fiber. Then this is just so this is just UI minus UJ. This one, UI minus UJ, and somehow, for example, if you put q equals 0 in this formula, so if we put, and so this is just CU, right? U1, U2, U3 are all the same, and then U cube is original Q. So therefore, this is somehow flat ring at q equals 0, and at q equals 0, you just get usual cohomology of P2. And so this is quite simple thing, but maybe this is somehow the main technical point in this talk. So actually, this can be somehow generalized to any toric varieties and even toric Drew-Mumford stacks. And in the case of stacks, it has some more subtlety along the log structure, along this large radius limit point, because large radius limit point can have non-trivial stabilizer, some orbifold group. So, but maybe I don't go into that. Yes? Sorry? C of Q modulo. Sorry, could you say it again? Just isomorphic to C of U. Yeah. So because I restrict to Q equals 0, then this is 0. Yeah, no relation, no other relations. So U cube is Q, and Q is 0. So this is usual. Yeah, so this is a CQ algebra. So this one, everything is over CQ. This is CQ algebra. And somehow Q is the product of U1, U2, U3, and now U1, U2, U3 are all the same, so U cube is equal to Q. And so somehow by compactifying, we can somehow see more closely what is going on in some sense. But maybe at this point, this might just look very easy thing. And so let me state the general setting of my main result. So general setting is that n is z to the n, or maybe possibly because I'm considering toric Riemann-Fock stack some torsion group, but maybe for the sake of clarity, just for the sake of exposition, I don't think about this part, and then just consider N to be free module. And S is a finite subset. S is a finite subset in N. And then I consider somehow the following sequence. This is some well-known, somehow very familiar sequence in toric geometry. So I send every basis associated with an element of S to B itself. So B is an element of S, and there is a basis EB associated with S, and that is sent to B. And
Spans or something?
sorry?
This finite subset span?
Yeah, let us assume that, yeah. Spanning N over Z. And this is a kernel of Peter. So it's defined to be the kernel of Peter. And in this setup, you can, so maybe you can, maybe I will give you an example later, but you can think of this as a sequence, standard sequence in toric geometry, which defines toric variety or toric obifolds or toric Riemann-Fock stacks. And then in this situation, some of the Hori buffer or given tau mirror is constructed as follows. So, so you just take, first you take the dual of this sequence. So maybe I just assume N is free. So Z to Z. L dual. And then tensor with C star. Then that gives you mirror family. So so maybe tensor with C star on this part. So you have C star to the S and L tensor C star. L dual, sorry. L dual to C star. And then have a W function W. W is a sum of coordinates as before, UB and S. So UB is a coordinate on the B factor of C star to the S. So this is somehow the general construction for the Hori buffer given tau mirror. Maybe you can think of this N as a lattice where our fan lives. And S is somehow the set of one-dimensional cones. So then again, somehow we want to have this kind of partial compactification. So there is some partial compactification. By the so-called secondary fan. Secondary fan, and this is somehow the following diagram. So you have C star to the S, mapping to L dual tensor C star, and this picture is now compactified to a picture from here to this, and function W is also extended to a regular function on a certain space Y. So Y and M are some. So this is due to Gelfand Kaplanov. Zelevinsky. And also in a more stacky situation, Dimar, Katarkov, Carr. So this is somehow now classical story, but you can somehow partially compactify these tori into some singular, possibly singular space. Y, M are somehow possibly singular toric, again toric DM stuff.
The fibers, do they change or just changing some hypertext?
The fiber of this one,
Yeah.
this map.
I think a point in
Yeah.
star cross C star, does the fiber change?
Yeah. Somehow this is like this. Somehow at the origin, the fiber is a union of three.
No, but what I mean is that if I take Q that's not at the origin,
Mm-hmm.
and I look at this fiber,
Mm-hmm.
is the fiber in Y
Mm-hmm.
a partial compactification of the fiber in C star
Mm-hmm.
cross S? Or
Sorry, maybe I don't understand. So you mean away from somehow the compactification, all fibers are just the same. So it's just a torus.
do not change
Yeah,
away from where you compactify?
yeah. So the fibers are just somehow N star tensor sister. So the first term. So yeah, this is just a family of tori, and then trivial family of tori compactified too.
Do you assume that the origin is inside the context of S or not?
No. It's quite general setup. So yeah, I think somehow in the regional context of their works, I guess somehow S is in a hyperplane of height 1.
That's not compact.
Yeah, in that case, yeah. But in my case, I think somehow in our case, we can take any S. Then, so maybe I want to mention somehow a few words about this partial compactification. This is somehow well-known story in GKZ work, but so yeah, so in this somehow compactification is in such a way that somehow if you take simplicial so-called stacky fan sigma on NR such that sigma 1 is contained in S. So stacky fan is in the sense of Borisov, Chen, and Smith. But yeah, maybe I don't recall the definition, but it is some fan in N together with the choice of the generators of one-dimensional cones. And I consider somehow simplicial fan on NR, which such that the generators of one-dimensional cones, this is generators of one-dimensional cones, they are specified in this context. This corresponds to one-to-one correspondence with maximal affine toric chart M sigma to Y sigma. So this somehow this is as a possibly singular toric stacks. Somehow this is covered by somehow finitely many toric charts. And the maximal charts are in one-to-one correspondence with a simplicial stacky fan, such that the set of generators of one-dimensional cones is a subset of S. And maybe I have some other conditions. Maybe I cannot quite clarify here, plus some other condition, but maybe I don't mention that.
Oh, yeah.
Ah, right. Right, that's right. Thank you. Thank you. So this is the wrong direction. So this is chart, I mean, somehow this is open chart. And this is all affine toric chart. And somehow you have some distinguished origin in this chart, which somehow corresponds to the large radius limit point of X in the mirror. So maybe maybe this is too much abstract, so I give you an example of this. So example. The first example is the following. So if I choose the following 3 points, this is the origin, and so I have somehow, if S is 3 points, these 3 points. This is 3 points in NZ2, and then I have two different structures, two different stacky fan. This and this, and so in the second case, I don't use this point as a part of the data of stacky fan. And this stacky fan, somehow, this is the usual fan, actually, gives you the total space of O minus 2 over P1. And this is a fan for the total, this orbifold, C2 mod mu2. And in this case, somehow, if I write the corresponding mirror, it is given by the following thing. So the corresponding mirror, sorry, maybe I should not split. Maybe I can perhaps still write here. So in this case, the mirror is like this. So Y is a space U1, U2, U3, such that U1, U2 is Q times U3 squared. And actually, I need to compactify slightly and to M. M is a P12, which contains Q. So actually, you can see that some of this somehow toric variety can be covered by two charts. Some Q equals 0. The chart near Q equals 0 corresponds to this, and the chart near Q equals infinity corresponds to this picture. And this is somehow the typical example where you have the crepant resolution of C2 mod mu2 by O minus 2 over P1. And the second example, this is another typical example for discrepant case. So, so in this case, I take 3 points like this, and I have either this fan picture or this fan picture, where in the second case I don't use the dot in the middle. So this corresponds to blow up of C2 at the origin, and this corresponds to C2. And the mirror is something like this. So the mirror is this is Y, this is U1, U2, U3. Somehow similar, but slightly different. QU3 is U1, U2. And this is somehow compactified, and this is over P1. M is now P1. So this maps to this. And the somehow chart near, this is a chart near Q equals 0. This is a chart near Q equals infinity. So these two are examples of this construction. And maybe more, in general, much more complicated, but essentially this kind of things. So, so our theorem with Courtian 10 is the following. So theorem 2016. So this says the following. So if you consider quantum connection of the toric stack associated with sigma, so sigma is X sigma is a toric stack associated with sigma, is a stacky fan, and this is isomorphic to the cyto, maybe I should say log cyto structure associated with a W, and restricted to the formal neighborhood of this chart, the origin of this chart. So this means a formal neighborhood of some of the large radius limit point of M sigma. And also somehow you have Poincare pairing here intertwines with the higher residue pairing. So I'd like to remind that some of this is formal neighborhood. So quantum connection in general is not known to converge, so it is just a formal connection. And so somehow, correspondingly, you also need to consider somehow restriction of W to this formal neighborhood of 0. And actually, somehow this is for big quantum cohomology. Big quantum cohomology. Not just small. So, so maybe our construction depends on the size of S. And you can also somehow take very big S, for example. So S has to contain sigma 1, but S maybe could be very big. And if you make S very big, then this is somehow this gives you the big quantum cohomology. Mm-hmm. This is non-equivalently true. So But maybe for the pairing, you need equivariant version. So because Poincare pairing doesn't exist non-equivariantly. So and then, and this is a first statement. And the second statement is that, sorry, I should have write the first statement over there. And the second statement is that this isomorphism is defined over the following ring. So, and somehow this is a little bit tricky point, and where U is an analytic open neighborhood of 0 of the large radius limit point. So, so in the above theorem, the above theorem is something like we are working over the ring like this. And whereas somehow the second theorem, second part of the theorem, some of this says that this is actually both sides can be defined over convergent power series ring, power series in Z, but convergent with coefficients in convergent power series in Q. And somehow the second part is somehow technical, but is important to understand the gamma structure for the quantum connections. As otherwise, somehow I cannot go away from Q equals 0, and it's a little bit difficult to talk about Stokes structure. But because some of these two rings have no, somehow they are not contained in each other, so they do not imply each other. And so now I want to consider somehow the geometry associated with these 1 and 2. So if I look at the Jacobian ring, the Jacobian ring. So, and how they change under these kind of transitions, so some birational change. So we consider spectrum of log Jacobi ring, W over M. So this is somehow in the work of Gonzalez and Woodward. They studied how quantum cohomology changes under Toric MMP. And maybe I can interpret their somehow result in this framework. So in the example 1, so Crepant example, so this example, in this example, what you have is the following. So I have just two fat critical points, some logarithmic critical points, and near Q equals 0, you have two critical points, Q equals infinity, two critical points, and maybe there is some blow up of critical points at Q equals 1/4. 1/4 is some singular line. And this is a crepant case. And the second case, which is discrepant case, like here, blow up of C2. In this case, so this is just elementary calculation. You can just somehow calculate the W. Maybe I don't write what is W, but W is the sum of U1, U2, U3. And then you see that in this case, you have, so Q equal infinity has only one critical point, and Q equal 0 has two critical points. So at Q equal infinity, one of the critical branches blow up, and somehow you can only see one critical point. That corresponds to the fact that the dimension of the cohomology of C2 is 1, whereas dimension of the blow-up of cohomology C2, dimension of the cohomology of the blow-up of C2 is 2. So this is something happens in discrepant case. So now more general case, somehow I just take some of the similar picture when you take a curve inside. Sorry? Vertical line. So at Q equal 1/4, somehow the critical point, I think every point is critical point, or at least somehow you have continuously many critical points. And so the Jacobian ring is infinite dimensional. So yeah. So now somehow this is somehow general, and you can maybe I'd like to say that somehow this kind of analysis is easier when you consider this logarithmic Jacobian ring. So for example, maybe you may want to compactify these pictures, like putting, for example, other dots over here or other dots somehow over there. Then you can get somehow compactified version. But so these pictures arises in somehow over the logarithmic divisor somehow. And over the logarithmic divisor, somehow quantum cohomology is almost some classical cohomology and easier to think. And now maybe I finish somehow with gamma conjecture. So more general situation. In general, well, choose toric invariant curve. And also which connects to toric stacks. Then somehow, maybe let us just concentrate on the second case, so discrepant case. So the theorem. So in this case, if you take quantum com bar, let us write Q com bar to be the completion in Z variable. So actually some quantum connection is actually somehow by this second part of the theorem, it is known to be convergent. And I somehow take a completion with respect to Z, not with respect to Q. Then, so in the discrepant case, that is somehow if canonical class of 1 is smaller than canonical class of K2. So in this case, you have the following result. this case, you have that quantum connection of x2 is a direct summand of quantum connection of x1. So this somehow generalized the Gonzalez-Woodward result to quantum connections. And some of the gamma conjecture is that this, maybe I'm sorry, this bar, sorry, quantum connection bar is, this means that completion with respect to z. Some of this is a direct summand. Then somehow gamma conjecture said that somehow there should be some semi-orthogonal decomposition of derived category. Maybe in general you may have this kind of decomposition which somehow induces this direct sum decomposition. And so this is just still conjecture. But there are several evidences, but which induces this decomposition, direct sum decomposition. Okay, thank you very much.